Okay, so hi everybody. I'll do this talk in English for ease of speech for me, but if ever you don't understand something or if I speak too fast, don't hesitate to ask me or tell me. All right. So I'm going to talk about TensorFlow, but more generally I'm going to talk about GANs, generative adversarial examples, networks. But first of all, I'm going to ask you one question. Who in this room have not seen the movie Matrix? Oh, so many. Okay. All right. So for those of you who have not seen the movie, I'm going to show you an extract, so it's a little recap. Do you hear?
Do not try and bend the spoon. That's impossible. Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon?
Then you'll see that it is not the spoon that bends. It is only yourself.
The Oracle will see you now.
All right, so for those of you who have not seen the movie, I'm going to explain a little bit what's going on here. And I'm not going to feel guilty about spoiling it because it's like 20 years old, so. But you should definitely see it still because it's a really good movie. So Neo is in the Matrix, and the Matrix is this huge software program that recreates the world around us. And we think we live in the real world, but we are actually living in the software. And so what the kid is saying to Neo is that there is no spoon because he is in the Matrix. And so even though he sees the spoon, he feels the spoon, he has the information that the spoon is there, there is actually no spoon. He's somewhere else sleeping. It works pretty much the same with artificial intelligence and models. Basically what happens is that you send an input to your model, and the model will have information of something, mathematical information, and it will think that something is there, but sometimes it isn't. Those are called adversarial examples. And we do use artificial intelligence a lot in our day-to-day lives. We have artificial intelligence in our phones, and we unlock them with face recognition apps. We trust them with self-driving cars to drive us safely back home. But are those artificial intelligence applications, are they really reliable? Today I'm going to show you how you can hack a neural network, and I'm going to show you how you can protect against attacks. So my name is Tiffany Souterre. Feel free to send me a message on Twitter. I'm also an organizer at the Google Developer Group in Paris, and I'm also a Women Tech Maker lead. So here, what do you see? It's a panda, right? It's a picture of a panda on your right, and Google.net, a image recognition app, recognizes this image as being a panda with a confidence of 57.7%. And now what do you see? It looks the same, right? The evil twin panda. And the exact same model actually classifies this image as being a gibbon with a confidence of 99.3%. But you can't see the difference between the two, right? Well, actually, the difference between those two images is some noise added to the image. This noise has been really carefully crafted by a model to confuse the model into seeing a gibbon when there's only just a panda. And it's been multiplied by a very, very small number, so the human eye cannot see the difference applied to the first image, but this difference is enough to confuse the model into thinking that there's a given. So this was published in 2016. It's pretty recent still, but it was a like big discovery. People were thinking, wow, what is going on? Like, how can we hack neural networks? It's so weird. And a lot of scientists tried other things. This is another publication. In this column, you see normal images, and here you see a noise that has been applied to those images, and all of those images on the right are the hacked ones. And all of the image on the right column has been classified as being ostriches by AlexNet, which was back then the state-of-the-art model for image recognition. So you might be thinking, okay, I can do this on images because I can tweak the value of pixels, but does this actually apply to the real world? When you print images with noise on it, you can still hack a neural network. Here you can see an example of a library that has been printed, and it's correctly classified as being a library. And with noise, it's now classified as being a prison. They do this example with other images, but you get the concept. You can print something and confuse them all like this. Another cool example is, so scientists were thinking, okay, we can create noise and confuse models. Wait, what else can we do? Scientists took a picture of Reese Witherspoon, here the actress, and they added noise around her eyes in the shape of frames, as if she was wearing glasses. But the perturbation was crafted in a way that she was then recognized as being Russell Crowe. And so it's a lot of fun, and then you're thinking, okay, what if I do 3D print those glasses and I wear them? What's happening? So when you 3D print those glasses, you can do different types of attacks on image recognition apps. You can do impersonation and dodging attacks. Here, you see that those two people wearing those glasses are doing dodging attacks, which means that they are not recognized as being faces anymore. They are invisible to the model. And the dodging attack here, the impersonation attack here, means that all those three people on the upper row are impersonating the people on the lower row, which means that this guy wearing those glasses is recognized as being Mila Jovovich. So if you know how to craft your glasses and you know how to 3D print them, you could basically be anything to the eye of the model. A last example that I really like is this 3D printed turtle. So scientists 3D printed two turtles, a control one that is a normal turtle, and it's recognized by Inception V3 as being a turtle. So that's cool. And they 3D printed another turtle with a little bit of perturbation on the shell, and it's now recognized as being a rifle, a lethal weapon. So this is fun here, but imagine that you can add perturbation on a rifle, and it's then recognized as being like, you know, a baguette or whatever. If you have cameras that have like security cameras that are supposed to detect when someone has a weapon, then this could be a problem. So I could just stop here and tell you that your image recognition apps can be hacked and you need to know it. But I wanted to show you how you can protect against it. And for that, I need to explain how neural networks work. So it's a really simplified way that I'm going to explain. It's much more complex now, but the principle is still the same. So here I took an image from the MNIST database. It's a database of handwritten digits, so people wrote numbers. And those images have been nicely standardized to images that are 28 pixels by 28 pixels, and it's black and white. So it's a nice data set to start off if you want to try deep learning. So all of the values of the pixels are defined by the color. So all the pixels that are black have a value of 0, all the pixels that are white have a value of 1, and everything in between is in the grayscale. So now, how do you build your neural network? you first have what we call an input layer. And an input layer is composed of all the neurons in your input layer will make up for all of the pixels in your image. So if you have 28 by 28 image, you will have 784 neurons because it's all of the pixels that you have in your image. And all of the values of those neurons will have the value of the pixel. In the output layer, you will have all of the different labels that your dataset has. So if you only have handwritten digits, all the possibilities that you will have as an output is 0, 1, 2, 3, 4, 5, 6, up until 9. So you have 10 different neurons in your output layer. And the value that will be in your neurons will be the probability of certainty of confidence of your model that the image that it's seeing is a 9. So let's say your model is well trained to recognize this as a 9, then in this neuron here, you'll have a value closer to 1. And for all of the other values, you'll have a value closer to 0. And all of the values need to add up to 1 because it's a probability. And in between, you have what we call hidden layers, and this is where all the math happens. So I'm going to tell you how to calculate the value for the first neuron in the first hidden layer, and then you'll be able to calculate the values for all of your neurons in your neural network. So the first thing you do is that first you sum all of the values of your pixels. And you multiply it by a weight factor. And the weight factor is determined by the model. And you add your bias term. And the bias term basically means that your neuron should not fire under this threshold. And because the sum can be very high or very low, you want your number still to be in between 0 and 1. So you squish this number between 0 and 1. And here I put the sigmoid function, but you have other optimization functions. And you do this for all of your neurons iteratively. And basically what you do when you do deep learning is that you have this huge vector of all of your values of your pixels, and you do a matrix multiplication with your weights. You add your vector of your bias terms, and you squish everything between 0 and 1. You don't need to remember all of those steps precisely to do machine learning. What I just wanted to show you is that deep learning is not a black box. It is just simply linear algebra. It's huge calculations, but it's very simple, actually. What's happening here is that actually you have a function that takes 784 values as an input, and it will spit out a vector of 10 entries long, and that's it. And so the vector here are the probabilities of certainty of each different labels at output. All right. So I wanted to give you a little insight of how you can actually picture it in space. So here is a representation of a model that would have only 2 features. So it means that 2 dimensions. It means that your picture here would be only 2 pixels. I could try to draw something in 784 dimensions, but it's like, you get it? I can't really do that. So a more simplified way to show you something is in 2 dimensions. But the concept is still the same. Here, imagine you have a data set, a training data set of, let's say, images of dogs, and this is the blue line, and of images of cats, and it would be the red line. And you want your model to draw a decision boundary. Basically, a function that would separate your data sets. And here, when you want to draw a straight line between your 2 data sets, the best separation you can do is this one. But you see it's not perfect. You still have blue images of dogs landing in the red area, and you still have images of cats landing in the blue area. See here? And this case would be if you only have 1 input layer and 1 output layer in your model. If you want to add complexity to your model, then you need to add hidden layers. By adding 1 hidden layer to your equation, you allow your decision boundary to go into another space. So it's not linear now, you can do a curve. If you curve your function, then you can more accurately separate your data sets and have a better model for this kind of function. So here is just with one hidden layer. Those two images are really interesting because here you see the separation, so the decision boundary from the perspective of the input layer. And here you see the exact same thing from the perspective of the hidden layer. And what it does is that basically the decision boundary is now a straight line, but it transformed the space for all of the other values. And this is basically what a model is doing while it's training. It's stretching the space in a certain way, and it squishes everything between 0 and 1, and it tries to draw a straight line between the two data sets, so it separates them, and it has a nice classification. See? So this is a really mesmerizing example. It's only in 2 dimensions, so you can get how complex it could be to separate data sets from more complex images. But yeah, this is basically what a machine learning algorithm is doing while it's training. It's applying transformation to the vector space. Oh, and that would be for hidden layers. So the more hidden layers you add to your neural network, the more complex transformation it can apply to the space, and the more things it can identify. So this is why we call it deep learning, because you have a lot of hidden layers between the input layer and the output layer. All right, so now that we kind of understand mathematically what's going on with deep learning, we can try to create our own, we can try to hack a neural network, right? So this is what I tried to do. And when I did that, I wanted to find which model I wanted to hack. So I had this comparison of models of top 5 error rates. The top 5 error rate basically tells you how for the first 5 top classifications that it's giving if it's doing a mistake, basically. So the lower, the better. And this is human performance. I put it here because a human was brave enough to go through the same data set that a machine would go through in order to assess its performance. So he was hand labeling all of those images. And nobody else did it. Actually, well, nobody else published it online. So I take his performance as granted for all of humans' performance. So we're around here, and all of the other top 5 error rates are a little lower, so it would mean that those models are actually performing better than humans at identifying things on images. So I took Inception V3 and I was like, okay, let's try to hack it. For your information, this is the architecture of Inception V3. Every single brick is a hidden layer. And the architecture is hugely complex. It's doing a lot of math, but still remember that this is only just linear algebra applied here. But the deeper, then the more precise you can be. And so ImageNet, not ImageNet, Inception V3 is able to recognize thousands of different classes. So the output layer is 1,000 neurons long. And the input for the standardized input for Inception V3 is an image that is 299 by 299 pixels, so that's a square. And 3 is the depth of the image with the different channels of colors, so R, G, and B. So I needed a guinea pig for my experiment, took a picture of my cat, and I wanted my cat to be recognized as being a spoon by Inception V3, because I thought it was a nice reference to Matrix. So the first thing you need to do with your image is to resize it. So, whoops, may I? Yeah. Yeah, there you go. You resize it to the size that the model is taking. And then you change the value of all of the pixels, because it's a big matrix, basically your image is a big matrix. And all of the pixels have a value between 0 and 255, so you need to shrink this between 0 and 1. And then I wanted to see the classification of my cat according to Inception V3. And the classification was a tabby with a confidence of 86.86%. So a tabby is a stripped cat. It's exactly what my cat is. And now I want my cat to be a spoon. So how am I doing it? How am I going to do this? Same thing. So you take your Inception V3 model and you transform your image as being the input layer. For now, my cat is still a cat to the eye of Inception V3. And I wanted to know the classification of the spoon for my cat. Because remember, in the output layer, you have all of the probabilities for the other labels. And when I check the classification of a spoon for my cat at the beginning, it was really low. It was 0.0 times 10 to the minus 6 something. So that meant that at the beginning of the experiment, Inception V3 was pretty sure that my cat was not a spoon. And it was interesting for me because I was thinking, okay, it seems challenging to make Inception V3 believe that my cat is a spoon. And the next following things that you need to do is, it's very verbose, but basically what it means is that you need to take your gradient and you need to take your learning rate. So basically what this code says is that while the confidence of my cat being a spoon is at least 98%, keep going through this while loop. And this while loop is basically taking the gradient descent. And the gradient descent is a function that gives you basically the direction towards which you need to go in changing your equation to go closer to the classification of the spoon. So you can't really visualize it because now it's in even more dimensions. It's 299 by 299 dimensions, so it's hard to visualize it. But if you visualize it in 3 dimensions, you have the classification of the cat, tabby, being around here, and the picture of my cat lands in this area, right? And we have the classification of the spoon landing somewhere far away, and the image of my cat is here. And I want my cat to land in the area of the spoon classification. So what the gradient gives me is basically the shortest angle towards which I need to aim to go to the decision boundary of the spoon. And it gives me the direction, but I don't know how far it is. And basically the white loop is what it's doing. It's telling me change a little bit every single value of my pixels to get closer to the decision boundary. And the step you need to take would be the learning rate. So the learning rate, basically, with the learning rate, you can give how far of a step you want to take in every single one iterations. Basically means you don't want to have a too high of a learning rate because you could overshoot behind the zone of the spoon, and this is not what you want to do, because then you would overshoot, and then your gradient descent would go back the opposite direction, and then you would overshoot again. You'd never land in the area of the spoon. And if you take 2 little steps, then it would take forever to get there, and you don't know how far the classification of a spoon is. You don't want this to run forever. So you need to empirically kind of guess what kind of learning rate you want to take in order to get to the area of the spoon. By the way, for my cat to be a spoon, it took me about 3 hours of calculation. It could be better with another learning rate, but I was happy with this time. So the first time I tried, I ran it overnight, and it was fine. At the morning, I had my spoon cat. So those are the results I got. The first one is the normal image, and the other 2 images are my cat being classified as being a spoon with confidence of 98.65% confidence. And the last one is the classification of a pineapple, because I had so much fun, so I tried other things. But I didn't want to burn my computer, so I just tried 2 different. But it's uncanny, because you see all of those images look very similar. I could barely see differences, and actually needed to convince myself that this was actually working. So I did another experiment. I took a complete white image, And I did the exact same experiment. I asked Inception V3 to change the values of the pixels in order for this white image to be classified as a pineapple. And this is what I had. Actually, you can see some of the differences, right? It's not very clear. So I took this image, the hacked image, into GIMP, and I put the saturation to 100% because I really wanted to see the differences. If you do this with a white image, you'll get a gray image, but I got this. This is all colored, it's not gray. It means that pretty much all of the values of the pixels had been changed. So the model was actually doing something. It was recalculating the space, so this image would land in the classification of pineapple, but I can't see a pineapple here. And at the time, what it meant is that even though the model is better than us at classifying cats or pineapple, it was unable to know what was a cat or a pineapple. It doesn't have the concept of it. It can't draw it. Or I should say it couldn't, because now it can. This is what I'm going to show you. But yeah, you know that you can hack neural networks. You know how to create your adversarial examples. Don't do it. But now I'm going to show you, because you're good guys, right? You want to protect your models against hackers. You're not hackers. If you want to protect your model against hackers, then you need to do GAN. A GAN is a generative adversary network. Basically, what it does is you need to create a twin model of your model, and you name one the discriminator and the other one the generator. And they're going to be best enemies. They're going to fight in a very long game. And the game is to try to confuse the other one, and the other one is going to try to know if it's confused or not. Basically, the first round of the game is you have a database of real images, like my cat, and you give it as an input to your discriminator. And the discriminator recognizes the image and says, I know that's a cat and that's a real image. And you reward your discriminator for being able to see it's a real image. And then that's the turn of the generator. And the generator generates a fake image of a pineapple. And you give it to your discriminator. And the discriminator is like, oh, I know what this is. This is a pineapple. But you generated it. You know it's not. So you label it as being a fake image. And then you punish your discriminator for not being able to see that it was a fake image. And you reward your generator for being able to fool the discriminator into thinking it's a real image. If you do this iteratively, thousands and thousands of times, the discriminator will get better at seeing that images are fake, but the generator will get better at generating fake images. What's happening is that at the end, if you do this with the MNIST database, computers are able to generate images like that. Those are not handwritten images by people. Those were generated by a computer. It was mid-training, so you can see that some of the shapes looks like a 9, looks like a 4. Some of them don't look like anything, but it's getting there. It's getting closer to, even for humans, into thinking that those were generated by humans, those are legit. Like, I couldn't really be able to tell you that this is a fake number. Here's a really nice publication of scientists that were basically showing the green line here is the performance of validation set error of a model that was trained on adversarial images. And when you show it adversarial examples, so fake images, it's doing less and less errors over time. It's getting better at seeing that those images are fake. While the blue line is the model that has not been trained with fake images, and it's constantly doing mistakes on fake images. And here is a really interesting thing. When you show it clean examples, which means real images, the model that has been trained with fake images is performing better than the one that has not seen fake images before. What this means is, and that's the take-home message of if you need to listen, it's now. If you need to listen one thing, it's that if you do a deep learning training always do it on fake images and real images, because not only your model will be better, but it will also be protected against fake images. Okay? Nice. Yes. And so it was tweeted last year by Jan Goodfellow, which was the father of the GANs, and it basically shows you the progression of how we can generate faces from 2014 to 2018, so it's even better now. It's uncanny, like it went so fast. I know very few fields where research goes this fast on research. But you can see like this image looks to me like it's a real person. Like you can barely say that she's actually generated by a computer. None of those people exist. None. And so at the time, like it was a year ago, like 2 years ago, I think, NVIDIA is doing a lot of research on synthesizing, generating those faces and images. And Philippe Wang, who was working at NVIDIA back then, created this website called thispersondoesnotexist.com. And if you click on it and you generate a new image, then the face that it's going to pop has been generated while refreshing the page. So, and every time you do it, there's a new face. So it has never been generated before, and nobody will ever see it in the future. They're all unique. And this is really cool. Just saying, it's really cool. If you want to try this website, it's great. For the little story, when this was out, it was a huge buzz. Everybody was talking about it. They were saying that artificial intelligence is going to take over. It's the end of the world and everything. And there were some kids on Reddit that wrote to Philippe Wang that if he could do the same thing with cats. So there is also this website called thiscatdoesnotexist.com. But he did it in a rush, and because the data set was not as clean as the human one, sometimes you get really cute kitties like this one, and sometimes you get really creepy kids, like, and you can try, like, it didn't take me long to find this one. It was creepy as hell. But every time you're gonna refresh the page, you're gonna see werecats with 6 legs. I don't know, sometimes they just have bottoms. It's weird, but it's a lot of fun. And also because the data set contains a lot of memes, sometimes the model will generate a meme as if artificial gets our humor. It's so fun. All right, we're gonna play one round. There's this website called whichfaceisreal.com, and you have to try to guess which one of the faces is real, which one of the faces has been generated by a machine. So who in this room thinks the right picture is the fake one? Okay, and so the left one is fake, so real, so right. You're correct, this was the real one. Let's try a new one. But vote more. Wait. Which one is real? Right? Left? Right, left. Yeah, you're correct. So as you can see, it's pretty good generating the face, but then you can see some glitches in the background. And usually I see that there's glitches, but still the faces, it's so incredible that like in 2014, it was 6 years ago, we weren't able to make those kind of faces, and now we are at this definition of details. It always surprises me. So yeah, why am I showing all of you this? GANs is really important in the field of research. Because now you see, before we were using image recognition apps to classify if the image has a dog, if the image has a cat or a plane, but humans can do it. We don't need a computer to tell us what's in the image, right? It's easy task. But now what we can do with GANs is asking much more complex questions to models. Ooh, sorry. Damn it. Qu'est-ce que j'ai fait? Ouais. We can ask much more complex questions now to models. You can ask, not only is there a cat in the picture, but you can ask, can you draw me a cat? Can you draw me a dog? But let's say you have a data set of molecules, because you're pharmaceutical companies, and you have molecules that can cure cancer, other molecules that are toxic, others that are not, and you can ask questions like, draw me a molecule that would cure cancer without being toxic. Or if you have blueprints of cars or blueprints of I don't know, spaceships, and you have ships that go really fast and other ones that use not much fuel, then you can ask questions like, draw me a blueprint of a car that would go really fast without using as much fuel. And GANs can help us design new solutions that we have not visited yet in the space of possibilities, because there's so many, but they can help us doing that. So it's basically, you could save the world with GANs, you can do amazing things with it, but you can also do very bad things with it. And it always depends on your ethics. Here, I'm going to show you an application that could be a really bad application of GANs is by generating deepfake things. Like here, whoops, sorry. Here you see that now GANs are able to take the face landmark of a person speaking. So it recognizes where the eyes are, the nose, and the mouth, and how it's moving. And it can apply those motions to a face where you only have the picture of it. So basically, you could make someone say something in a video when you only have the picture of that person. And you need to know that, because now with the edge of fake news and fake videos, it is possible to make someone say something that they did not say. So be really careful with that. It could be a really bad application of that, but one really cool application that I wanted to show you, because the video is long, is that they made the Mona Lisa speak. Isn't that great? I love this. And they have other examples, like Einstein is speaking also. This is really cool. So yeah, applications of GANs can be really incredible. Please, if you do deep learning, have ethics. Think about your applications and the impact of your work on other people and on the society. Thank you very much. If you have any questions. Yes?
Well, you transformed your cat into a spoon, but what was the percentage of recognizing your cat as a cat after you changed it to a spoon by the neural network?
You mean if I took the picture of my cat hacked into a spoon, then could I remake it as a cat?
What was the percentage of the recognizing?
The cat? I actually did not check, and someone asked me, and I never went back to my project to see it was a classification of a cat. I don't know.
Like, does it change anything on because the percentage was like 86% as being a cat?
Yeah, it was 86%. But see, I could guess something, is that because all of the values need to add up to 100%, and the classification of my cat being a spoon was 98 something, then it was less than that. It necessarily had to be less, but I don't know, maybe 1%, 0.5, I have no idea. I'm sorry. Yeah. Apéro. No? Oui.
Do you have any idea of the cost of computing a deep fake like you showed for videos? Is it something that it is economically unreachable right now so that it's not commonplace? And yeah, does the economy of it prevent broad usage?
I don't think it's unachievable, unfortunately, because you only need the model to be trained already. What's completely expensive is the training part. If someone has trained a model already and it's available, and I'm pretty sure it would be at some point available online, anybody could take the model, and then the only compute time that you have is the prediction, which takes almost nothing. Yeah. So it's achievable to anyone, unfortunately. Yes? Okay. Thank you very much.